In this video, I'm going to go over 5.1 to 5.3 guided notes, and we'll be talking about solving inequalities. So first, I want to talk about equality. So equality, or an equation, has the word equal in it. And so, as we know, an equality or an equation, which is what we've been working with over the past several weeks, it's a mathematical statement showing that two things are equal. So the symbol that we use to show that two things are equal is the equal sign. You've been using this symbol for many, many years now. And so an example would be something like x equals -5. And we could graph that on a number line. I'm going to plot my own numbers here. I'm going to put the 0 a little bit over to the right so I have enough space for -1, -2, -3, -4, -5. You could go on to -6. And then on this side, I have +1, 2, 3, and so on. So if I'm saying that x equals -5, that means that x equals -5. This is where the solution exists, is right on -5. It means that x does not equal 0, that's not a solution. X does not equal anything else except -5. So this is something that we should be pretty familiar with, is the idea that something is equal to something and what that means. What we're going to learn about now is inequality. So as it would sound, it's unequal. So it's a mathematical statement showing that two things are not equal. Okay? So sometimes this is represented just by the symbol. This is the not equal sign. So you could say that something is not equal to something else. But there's other statements of inequality, and you've probably worked with these as well for many, many years. So the first one is the less than, the idea of less than. So we're not saying that something is equal to, but we're saying that the answer, the solution set, is less than a certain amount. And so the less than symbol looks like this. Oops, just do it like this. You can think of it as an L, just a little bit squished down. So it's like an L shape, but squished down. That's the direction that it faces. An example of a less than inequality would be saying that x is less than 3. And so the way that we would graph this on a number line is we also need to think about a couple other symbols. If we are dealing with less than, how we graph that is that we use an open dot. So I'll put that, I'm going to back up here. We'll say less than, and then you would use an open dot on your number line. What that means is your answer, the actual number that it's on, it has to be less than that. So it does not include that actual value. So if x is less than 3, x doesn't equal 3. It can't touch 3, but it's anything less than. And so we can also use the symbol as a guide for us. See how the less than symbol is pointing to the left? So this is how I'm going to graph it. I'm going to graph with an open dot, and then I'm going to draw my arrow to the left because the symbol here is facing to the left. And this only works when it's set up like this, with like the variable on the left-hand side. So I need to once again number my number line. So 0, 1, 2, 3, 4, -1, -2, -3, -4. And so I'm using an open circle on 3, and then my arrow is pointing to the left. So this is very different than equality, what we were talking about before, where we just have one answer. It has to be -5. But here we're saying that our answer could actually be anything less than 3, all the way to -infinity. But what this is also saying is x cannot equal 3. So we can get very, very close to 3. Our answer could be 2.5. Our answer could be 2.999, but it does not go up to 3. It doesn't include 3. Anything less than 3 will work. And then, of course, anything greater than 3 will also not work. It's not part of the solution, but anything less than 3 will work. So the same is true, just the opposite, with greater than. So the greater than symbol is facing the other way. And similarly, it has an open circle on the graph because it's just greater than, it's not equal to that value. So if we had x is greater than, x is greater than negative 12, if we had x is greater than negative 12, I would want to set up my number line so I can go to negative 12, which is going to be down here. I'll do like negative 13, negative 12, negative 11, 10, 9. Okay, so my open circle is going to go on negative 12, and x has to be greater than that. What that means is my values are going to be to the right in the positive direction. To the left is in the negative direction. To the right is positive. These numbers are getting increasingly more positive. They're getting greater. So as we move to the right, this is my solution set here. And anything in this area, anything greater than 12 is a solution to this inequality, but not negative 12 itself. So negative 11.5, negative 11.99999 will work, but 12 is not part of the solution set here. And then obviously anything left of 12 is not a solution as well. Then we get into the idea of less than or greater than or equal to. So this is slightly different. If we have less than or equal to, we have the less than symbol, but we also have half of the equal to symbol. So that means that our value is less than or equal to that value, meaning it's included. So we use a closed dot to show that that value is included. So in this example, we have x is less than or equal to negative 1. So I'm going to set up my number line here. I'm going to make sure that I have negative 1 on there. So I'll do 0, negative 1. And to the right. So we have that x is less than or equal to. So we're going to put a closed dot on negative 1 because the answer can be equal to negative 1, but it can also be less than. Less than meaning, look where that arrow is pointing. It's pointing to the left. So my arrow is going to go to the left here. And so my answer could be anything less than negative 1 or including negative 1. Because we have that closed dot, it could also include that value. And so the same idea holds true when we're doing greater than or equal to. The symbol faces this way and also has an equal to. And the dot would be closed because it includes that value. And so an example here would be x is greater than or equal to 7. So I could have 7, 8, 9, 10, and then I go back this way, 6, 5, 4, 3, 2, 1. And so here I have my solution, x has to be greater than or equal to 7. So I'm going to put a closed dot on 7 because it can equal 7, but it's also greater than 7. So to the right is where I put my solution. So anything to the right of 7 is a solution. So 7, 7.1, 8, 9, 10, anything works. But anything to the left, 6, 6.5, 6.8, 6.9, those are not solutions to the inequality. So now we are going to talk about how to solve inequalities. We've worked with solving equations, but we also need to be able to solve inequalities. So the steps for solving an inequality are going to be very, very similar to solving an equation. So inequalities can be solved in the same way as equations. So we're going to use these ideas we've already worked with, the inverse idea of inverse operations. So what that means is addition and subtraction undo each other, and multiplication and division undo each other. And we're also going to be using the golden rule of algebra. And what that says is what you do to one side, you must also do to the other. And I'm just going to put a little note here and say, I need to see this work shown. As we've been solving equations, some people use alternative ways to use inverse operations, but they're not showing that they're doing the same thing on both sides. You must show that work, that you are actually doing the same thing on both sides, and that you're keeping the equation or the inequality balanced. I will be taking off points if I do not see you doing the same thing on both sides. So that's just something to keep in mind. There's just one exception. So we're going to come back to this in just a second after we do a little investigation here. There's one exception, though, in solving inequalities, how it's different from solving equations. So we're going to actually work with an example here, and we're going to figure out what that exception would be. So here I have a statement. 4 is less than 6. Shows on a number line, 4 and 6 both. And we can see that this is true. It's showing us in purple down here that smaller numbers are to the left, so it's getting more and more. We could continue this. 2, 1, 0, -1, right? It continues. And to the right of 6, these numbers are getting larger and larger. 6, 7, 8, and they're getting more and more positive. Down here, we're moving in the negative direction. So that's just important to kind of point out what we're working with here. And so this is a true statement. 4 is less than 6. That's true. So now we're going to kind of play around and see what happens when we use different operations. So first we're going to add 4 to both sides. And I'm going to see what my outcome is. I'm going to see what happens when I do that. So what I have is 4 plus 4. If I add 4, I get 8. And if I add 4 to this side, 6 plus 4 is 10. And my symbol, I'm going to keep the same, less than. 8 is less than 10. Is this true or false? Well, it's true, right? 8 is less than 10. That's a true statement. So this is true. So it seems that if we add something to both sides, it remains true. There's no problem. So yes, we can add something to both sides and it will remain true. So it's fine to do that. So let's do the next one. Instead of adding 4 to both sides, I'm going to subtract 5 from both sides. So let's see what happens if I subtract 5 from both sides. So 4 minus 5 is -1. I'm going to keep my symbol less than. 6 minus 5 is a +1. Is -1 less than +1? Yes, that is true. So if I subtract something from both sides, it seems like it will remain true. There's not any problem there. So yes, we can subtract something from both sides and it's going to be fine. Let's go to the next one. Multiply by 3 on both sides. So let's see what happens when I multiply by 3 on both sides. 4 times 3 is 12. I'm going to keep my symbol less than. 6 times 3 is 18. Is 12 less than 18? Yes, that's true. 12 is less than 18. So nothing happens. Everything remains true when we multiply by 3 on both sides. We have no problems. Let's do the next one. I'm going to divide by 2 on both sides. So I'm going to divide by 2. 4 divided by 2 is 2. Keep my symbol less than. 6 divided by 2 is 3. So do I get a true statement here? 2 is less than 3? Yes, that is also true. So it seems like dividing by a number, dividing by 2 made a true statement. It's fine. There was no problem there. So let's see what happens here. We're going to multiply or divide by -1 on both sides. So multiplying and dividing by -1, they mean the same thing. So I'll multiply by -1. So -1 times 4 is -4, and put less than, and 6 times -1 is -6. And I'll show you the exact same thing happens if we divide. It means the same thing. I could divide both sides by -1. So 4 divided by -1 is -4. 6 divided by -1 is -6. So it doesn't really matter if we multiply or divide. So let's check out this statement. -4 is less than -6. Is that true? That actually is not true. If we look at it on a number line, and we have -1, -2, -3, -4, -5, -6. -6 is down here, and -4 is up here. So actually, negative 6 is less than. Yes, I understand 6 is a bigger number, but negative 6 is further negative. It's less than negative 4. So this is actually not true. This is false. So we have an issue here. If we're multiplying or dividing by a negative 1, we got a false statement. So let's see if I multiply or divide by another, possibly, it looks like it's the first time I've been doing a negative, so let's try that. If I divide by a negative 2, let's see what happens. So 4 divided by negative 2 is negative 2, less than. 6 divided by negative 2 is negative 3. Is negative 2 less than negative 3? No, that's actually not correct as well. So we can hopefully see here that multiplying or dividing by a negative causes some problems when we're working with inequalities. And so this is the rule that we have to remember. There's just one exception, and that is when you're multiplying, when you multiply or divide by a negative, you must flip the inequality. So what that means is, if we look back at this example, how could I make this statement? Negative 4 is less than 6. That's not true. But what is true? Well, negative 4 is actually greater than negative 6. So we have to, anytime we multiply or divide by a negative, when we multiply or divide by a negative, we have to flip the inequality. And that's just a rule that we're going to have to remember. So now we're going to get into some examples of solving inequalities. So if I look down here, for the first one, I have x minus 8 is less than or equal to negative 6. So like these instructions say, I'm going to solve these the exact same way I would solve an equation. I'm going to use inverse operations, golden rule of algebra. But if I multiply or divide by negative, I have to flip the sign. So here I've got x minus 8 is less than or equal to negative 6. I'm going to identify my variable, which is x. I've got x minus 8. In order to undo a minus 8, I'm going to add 8. Remember, adding is fine. It's not going to cause any problems. Negative 8 plus 8 cancels. And this is what I mean by showing the golden rule of algebra. Watch how I'm showing that I'm adding 8 to both sides. This is unacceptable. And this is work I'm seeing from some people. I'm seeing in the next step this, and you're not showing me how you're getting rid of this. That's a problem. You have to show the work like this. Plus 8 plus 8. I need to see that you understand that concept of keeping the equation balanced, or the inequality. So negative 8 plus 8, that cancels, leaving me with x is less than or equal to negative 6 plus 8 is 2. So x is less than or equal to 2. And then the directions don't say so. There are actually no directions, but we want to graph this to show what that would mean. So on my number line here, I'm going to make sure I cover the numbers that I need to cover. I start at 0, 1, 2, 3, negative 1, negative 2. X is less than or equal to 2. So I'm going to put a closed dot on 2 because it's less than or equal to, and my arrow is pointing to the left. X is less than. So my solution could be anything less than 2 or anything equal to 2. It could be 2 itself. All right, here's the next one. I've got negative 12y is greater than or equal to 48. My variable here is y. I have negative 12 times y. So the inverse operation of times would be to divide by negative 12. So this is where I want to be careful. Negative 12 divided by 12, negative 12 cancels, leaving me with y. However, I'm dividing by a negative 12. Dividing by a negative. So when I do this, remember, it's going to cause a problem. I need to flip my inequality symbol in my next step. So y is not greater than or equal to, y is less than or equal to, and 48 divided by negative 12 is negative 4. So I had to flip the sign. I flipped it to go the other way because it would not be true if I kept it that y is greater than, because I divided by a negative number. So this is the solution. Y is less than or equal to 4. And I'm going to go ahead and graph this. I want to make sure I include values to the left. And y is less than or equal to, so I'm going to use a closed dot on negative 4. And if it's less than, I'm going to go to the left. So my solution could be anything less than negative 4. Looking at this next one, I have 3a minus 15 is greater than 4 plus 5a. This one's a little bit more complex because I have variables on both sides. I have 3a on the left and 5a on the right. The first thing I need to do is get those together. So thinking one step ahead, in order to keep my a positive, I'm actually going to subtract 3a from both sides. Notice how I'm showing that I'm doing this on both sides. 3a minus 3a cancels, leaving me with a negative 15 is greater than. Now, so far I've just subtracted. Remember, subtracting is fine. So I just keep my sign. 4 plus 5 minus 3 is 2a. Now I want to work again on getting this by itself now that it's all together. First thing I'm going to do is subtract 4 to get it away. Remember, subtracting is fine. I don't have to do anything to the sign, but I am showing that I'm doing this on both sides. 4 minus 4 is 0. Negative 15 minus 4 gives me a negative 19. It's greater than 2a. Finally, to get the a by itself, this is 2 times a. The opposite of times is divide, so I divide both sides by 2. And I'm left with a. Now, I divided by a positive, so once again, I don't have to flip the sign. It's going to stay the same. And negative 19 divided by 2, 19 can't be evenly divided by 2, but 18 can. Negative 18 divided by 2 is negative 9, so this is going to be negative 9.5. So here's something we also need to be careful about. This is saying that negative 9.5 is greater than a. So what that means is a is actually less than, look at the way the sign is pointing, a is less than negative 9.5. For equations, we would leave it sometimes, but for inequalities, it's actually probably helpful for us to go ahead and switch it so that the variable is on the left, because it's going to make graphing easier. I'll show you what I mean. When we make this graph, negative 9.5, I'm just going to do negative 12, negative 11, Nine and a half is between the negative 9 and the negative 10, and it's less than, a is less than negative 9.5, so I want to use an open circle at 9.5, and a is less than means it's going to point to the left. This can get confusing. If you left it like this, you might think that the arrow is pointing to the right, but that's not true because it's saying negative 9.5 is greater than a, meaning that a is actually less than 9.5. It's to the left. So that's why it's a good idea to go ahead and flip it with inequalities. So that's the solution. And then we've got one more. This one is even more complex because we have variables on both sides and they're inside parentheses. So we've got 6a on the left and 4a on the right. Oh, I've also got a 3a out here. So I'm going to have to first use the distributive property here. So then this is a negative 2 times 6a minus 4, so I'm going to pass that out. And on this side, at 4 minus, remember this is like a negative 1, I have to pass out this negative 1 to distribute that through. So let's go ahead. 3a, it's going to just drop down. I have negative 2 times 6a is negative 12a. Negative 2 times negative 4 is a positive 8. I haven't done anything, I haven't moved anything from one side to another, so the symbol stays the same. It's less than 4 stays the same. -1 times -4a is -4a. -1 times 6 is -6. So I distributed, I got rid of my parentheses. Now I want to combine all my a's. I've got 3a minus 12a. Those are on the same side, so I'm just going to combine them. I'm not moving it to the other side, so I just do what it says. 3a minus 12a is -9a. I keep the plus 8. It's greater than. And then also on this side, I'll go ahead and do this. I have my -4a here, but then I have a 4 minus 6. Those are like terms, so I can go ahead and just combine those. 4 minus 6 is -2, and then I have -4a. So now I still have a's on both sides, but I simplified the left and I simplified the right. Now I'm ready to start crossing things over to the other side. So in order to keep things positive, I'm going to move this 9a by adding it to both sides. -9a plus 9a will cancel, leaving me with 8 is greater than -2, and then -4a plus 9a is a positive 5a. Now that my a's are all together, I want to get them by themselves, so I'm going to add 2. Remember, all we're doing so far is adding and subtracting, so I don't need to flip anything. 8 plus 2 is 10, is greater than 5a. And then finally, to get this a all by itself, I'm going to divide both sides by 5. So 10 divided by 5 is 2, is greater than 5 divided by 5 is 1a. But once again, we want to get our variable on the left just to make graphing and understanding this easier. So what this means, if 2 is greater than a, what that means is a is actually less than. What I do is I look at where this is pointing. A is less than 2. And so that's how, these mean the same thing, but it's easier if our variable is on the left, because then I can just see my arrow is going to point to the left when I graph it. So here's a graph. I want 2 on the graph, so I'll just go 0, 1, 2, 3, -1, -2. If a is less than, I'm going to have an open circle on 2 because it doesn't include 2, and my arrow is going to point to the left. It's less than 2.